Okay. So where were we? So I tried to introduce the so-called the elementary matrix. So elementary matrix is an n by n matrix that looks like this. And what is the law of multiplying n by elementary matrix? So if you multiply elementary matrix to the left of any other matrix, then it is going to perform a so-called the elementary law operations. Multiply the L times L times J's law and add it to the i's. So that is what elementary matrix is. Okay. So this is an elementary matrix. So using these elementary matrix, I will try to introduce I will try to show you how to perform the fourth elimination using these elementary matrices. Okay. So we were about to solve any given system of linear equations. But in matrices, this is a system of linear equation. So, well, if your A is n by n matrix, and my X is n by 1 matrix and B is n by 1, then this matrix, well, this is a matrix equation, but in other words, this is a system of linear equations, especially that has n unknowns and n equations. So, being able to solve any given system of linear equation is equivalent to say, solve this matrix equation for X. So if you can solve this matrix equation for X, then so that is mathematically equivalent to say to solve the given system of linear equations. This is our example. If this is A and this is X and this is B. So A and B is given and you are supposed to solve X1 and X2, X3. All right, so and last time, so in order to solve any given system of linear equations, then you need to do so-called the elementary law operations. So I mean, in other words, fourth eliminations. And by fourth eliminations, I mean by eliminating these three indices that lives below the diagonals. So getting rid of these three guys is the fourth elimination. So how do we do the fourth elimination in this case? No, not like this. So this is my original matrix A, and in order to do the Gaussian elimination, then I will need to multiply. I will need to multiply the first law by -2 and add it to the second, and first law multiply by this guy by 1 and add it to the third. Then for future purpose, I will just keep record of every single elementary law operations. So -2 to the first and add it to the second, and 1 to the first and add it to the third. Then I have 2, 1, 1, 0, -8, -2, 0, 3, and 0, 8, 3. Okay. Now my next target is this entry. I will need to eliminate this one. To do that, I multiply 1 to the second row, and add it to the third. Then, yeah. In the first and second row they just carry over, but the last row is 1. So this is the end of the fourth elimination, right? Okay. And during this procedure, I have performed 3 elementary row operations. This one first, this one second, and this one is the last. Okay. Now, I am writing this everything in terms of the matrix multiplication. This is my original matrix A. This is my matrix A, right? And I have performed these elementary row operations. This one has to be performing this elementary row operation is equivalent to multiply the this matrix. These dot implies there is so entry equals to 0. So if entry equals to 0, then I will just leave it as a blank or just put it this small tiny dots. So this elementary operation is achieved by multiplying this elementary matrix to the left of your original matrix A, right? Now, to do that, then I multiply another elementary matrix. This is first to the third, which 1, and so like this, okay? And for the last one, I need the second one to the second and add it to the third. So this is third row and second columns, and the entry must be 1. Okay. So suppose that I have multiplied these 3 elementary matrices to the left of original matrix A. Then the result has to be this, right? Because I have performed so I have performed exactly the same row operations as I did. So therefore, the result has to be the same. Okay. All right. Great. Before I move on, so let me multiply these 3 matrices. Let me multiply these 2 first. This guy by this, I have, sorry. This guy times this, I have what? Multiply this matrix by this elementary matrix means that I multiply by 1 to the first row. I have 1 here. That means I multiply 1 to the first row and add it to the third. So multiplying these 2, I will have this, right? I have multiplied 1 to the first row and added to the third. So the answer must be this, okay? And I am multiplying this matrix to this elementary matrix to this. So multiplying these two, I have so this is what I have one in this entry. That means I multiply the second row of this guy by 1 and add it to the third. That must be the result. Then it has to be okay. This one must be the result of multiplying these three elementary matrices. Right? Okay. Yeah.
Why minus 1?
Why minus 1 here?
Yes.
Oh, because I have 1 in the third row and second entry. Multiplying this elementary matrix by this implies I am performing the elementary row operation such that multiply 1 to the second row and add it to the third. So multiply, but this guy multiply by 1 and add it to the third. And so minus 2 plus 1 must be minus 1. And this one, 1 plus 0 is going to be 1. Okay, good. Computation is really important. So I will spell out many different theorems and propositions and theories about the linear algebra. But what is the point of learning the linear algebra? So being able to compute something. So even if you know many theories, but you cannot compute anything, that the entire thing is pointless. So just being able to compute, that is the key aim of the linear algebra. So okay, anyway, I think this is the right time to introduce the notion of the upper triangular matrix and the lower triangular matrix. What is the upper triangular matrix? So suppose that I have some square matrix. So A is the square matrix, and if all entries above the diagonals are 0. So once you have a square matrix, then what is the diagonal entries? These entries, they are called the diagonal entries. And if all entries above the diagonal, so if all these number entries are equals to 0, then we say my matrix A is a lower triangular matrix. Okay, very intuitive naming. And by the same way, if any square matrix satisfying this property, so every entry below the diagonals are 0, then we say that matrix is a upper triangular matrix. Okay, so this is what I mean by lower triangular matrix and upper triangular matrix. For instance, this matrix is a upper triangular matrix. Okay, and these matrices, they are all lower triangular matrices. Also there is a diagonal matrix. What is diagonal matrix? Diagonal matrix is a matrix that is at the same time, diagonal matrix is upper triangular matrix and lower triangular matrix. So if any square matrix is a simultaneously upper and lower triangular matrix, then matrix must have, so if the diagonals are all, all the off diagonal entries must be 0. So that is what I mean by diagonal matrix. Okay. And there is very interesting properties regarding the lower and upper triangular matrices. Suppose that you try to multiply two different lower triangular matrices of same dimensions. Just like this. Then, interestingly, if you multiply two lower triangular matrices, then the result is another lower triangular matrix, lower triangular matrix. Why is that? I will show you by this tiny silly example. So suppose that I am taking the inner product of the second row and the second column. Then so taking the inner product of these two will be the 2 and 2 entry of the resulting matrix. Okay. And if I multiply 0 by this, again 0, and this guy by that, with some number, it should be some number, but this guy by this, again 0, and this guy by this, again 0. So almost everything equals to 0, but this guy times this. So that number is going to be here, right? But however, if I multiply this row by the third column, then this number times this equals to 0, and this number times this equals to 0, and this number times this equals to 0. Everything equals to 0. So therefore, you are guaranteed to have 0 on this entry, right? Just try to spend a little time playing on these lower triangular matrices. Then I guess you are easily be convinced that multiple of two lower triangular matrices is another lower triangular matrix. And same is true for the upper triangular matrices. So if you multiply two upper triangular matrices, the answer is the upper triangular matrix. So I mean, in other words, the space of all lower triangular matrices is closed under matrix multiplication. Okay, good. Also, there is very interesting property going on here. Assume that I have this looking elementary matrix. So this is an n by n elementary matrix. And for this elementary matrix, I have multiplied another elementary matrix to the left of this elementary matrix. And I am claiming that the answer is the identity matrix. Are you convinced? Yes, no, maybe? Okay, I will try to explain. So, well, okay. Having this elementary matrix is the same as you perform an elementary row operation such that you multiply L times J's row and add it to the I's row. This is what I mean by multiply by this elementary matrix. Okay. And I have multiplied another elementary. This is another elementary matrix, right? But this time around, so what is the purpose of this elementary matrix? You multiply negative L to the J's column and add it to the I's. So which is precisely undoes this elementary matrix, right? So therefore, you multiply by L and add it to the J's, I's, and you multiply minus L and add it to the I's. So therefore, you did nothing. You did no elementary operations. Therefore, this guy times this must be the identity. Okay. And on the other hand, so this guy times this is again must be identity, right? All right, good. Very interesting property. Now, this is the right time to introduce the notion of the inverse matrix. Okay, why spend time writing down all these propositions? Because all right, this is my definition of the inverse matrix. Suppose my matrix A is an n by n square matrix. Inverse, okay, by the way, inverse matrix is only defined for the square matrix. For non-square matrices, for any rectangular matrices, then there usually there cannot be any inverse matrix. So inverse matrix is only defined for the square matrix. Suppose that I have an n by n matrix, and if I can find another matrix B such that B times A equals to A times B equals the identity matrix, then we say A is an invertible matrix, and we write A superscript -1 is the B. So what this notion is the inverse of A. And so A in this type is usually called the inverse or inverse matrix of A. So this is exactly the same as the inverse of multiple of two numbers. So if you have number system, and if you multiply any multiplication inverse of any number is usually denoted by any number to the -1. So same convention is true for the Waldorf matrix. Also there is very interesting question. So in the Waldorf number system, not every number allows its multiplicative inverse. So I mean, precisely speaking, the 0 doesn't have any multiplicative inverse. Same is true for the matrix. So there are some matrices that doesn't allow any inverse matrix. So very special. So there and almost all matrices allows its inverses, but there are some very special matrices that doesn't have inverse. We'll talk about that issue later. But anyway, so you should be aware that not every square matrix allows its inverse. But if A has an inverse, then we say that matrix is invertible matrix. Okay. Now, using this terminology, maybe I am safe to say this matrix is the inverse of that matrix, and vice versa. This guy is the inverse of this. So these two matrices, they are inverse matrices. So in other words, for any given elementary matrix, taking its inverse matrix is very easy. Just take the opposite side. That's it. Okay. Now, why am I interested in the inverse matrix at this point? Let me just go back to this. This was my original matrix A. And I will denote this matrix by U. Clearly, U stands for the upper triangular matrix. And well, for simplicity, I'm going to say this is E, this is F, this is G. Yeah. So, well, simply speaking, G times F times E times A is U. But you should be able to see that these three matrices, they have inverse matrices. So what if, so this is my matrix equation. A is U. But what if I multiply E inverse times F inverse times G inverse to the left of this matrix equation? This is also true, right? Now, G inverse times G. So this one must be identity. So I'm free to cancel these two guys out. And same is true for this, and same is true for this. So in other words, A is E inverse, F inverse, G inverse times U. Okay. Good. Let me multiply this. Okay. What is E inverse? This is E. Therefore, E inverse must be, just take the opposite sign. This is E. This one must be E inverse. And by same way, F inverse must be this. And E in G inverse must be just like that. Okay. And everything is followed by this upper triangular matrix here. Okay. Good. All right. Okay. I really want to spend enough time trying to multiply these three matrices. Okay. Let me do this one by one. Well, multiplying this is again another elementary matrix, right? So multiplying this elementary matrix to the left of this guy means that I will need to multiply -1 to the first row of this matrix and add it to the third, right? So multiplying these two, I have one, right? Yes, yes, this is good. Now I multiply these two, then I will get, so this is another elementary matrix. So multiplying this matrix to the left of this implies that I multiply the first row of this matrix by 2 and add it to the second. Then it has to be 1, 2, 1, right? Right? Yeah. Good. So far so good. 네네네. 이게 간단한 그러니까 이게 elementary matrix를 곱한다는 게 그러니까 여기 지금 3 this entry -1. So this entry is located at the third row and first column. So this means the column index implies I multiply this number to the first. This is the first row of this matrix. So I multiply -1 to the which row? Since this guy is located in the first column, so I multiply -1 to the first column of this matrix, and which sorry, and which row? This is third row. Therefore, -1 times -1 has to be added to the third. This is what I mean by multiplying elementary operation. 그러니까 이게 3,1 엔트리에 -1 있잖아요, 그렇지? 그러니까 그러니까 여기 3,1, 1이잖아. 그러니까 첫 번째 로우에 -1 곱해서 세 번째에 더해라 그 뜻이잖아, 그렇지? 그러니까 여기에 -1를 곱한 놈 여기 더한 거야. 그러니까 -1 나왔지. Okay? Good. And I have 2 on the second row, first column. That means I multiply 2 to the first row of this guy and add it to which row? Second row, because this entry is located on the second row. Therefore, this is why. So therefore, 2 times the first one and add it to the second. So therefore, I get this. Okay. Okay. Good. Bad? No? Maybe? I know that you guys are really smart. You guys are so smart so you're admitted to this institute. So if you're not following me, then maybe that is not your fault, but that should be my fault. But if you spend a little time working on these elementary row operations and multiplying elementary matrices, then you won't have too much trouble convincing yourself why this multiple of these three matrices equals to this one. Okay. I told you that I really want to spend enough time computing the multiple of these three matrices. This is so important. Why is it that important? Because the entry I get here, 2, -1, -1, is precisely the same as these entries, right? Which was not true in the previous example. Let me go back. So previously, I tried to multiply these three elementary matrices in this order, but the resulting matrices have indices which was different from the original one. So in particular, this guy was different from this one. So entry of this guy. So if you multiply the elementary matrices in this order, then in order to get the entry of the resulting matrix, then all you need to do is just multiply everything one by your hand. This is so painful procedure. But if I multiply these inverse elementary matrices in this order, then you can be convinced that you should be able to convince yourself that in this order, the computation of these entries is very easy. Just copying and paste these entries one by one and insert it to the corresponding entries. That is how you get the entries of this resulting matrix. Why is that? Why? Because in this order, if you multiply in this order, you can convince yourself that elementary row operations in this order does not affect the previously determined entries. But if you perform the elementary row operations in this order, then the previously determined entries can be affected by future row operations. That is why computation of this order is hard, but computation of this order is easy. Okay, good. So by the way, so I was able to write down any matrix A as a multiproduct of this lower triangular matrix times upper triangular matrix. I'm going to call it this guy. I will denote this matrix by L and this matrix by U. So in other words, A is a product of L and U. So I was able to write down any given square matrix A as a product of lower triangular matrix times upper triangular matrix. And in particular, this lower triangular matrix, the diagonals of this lower triangular matrix is all ones, right? So this is some sort of factorization. Do you remember the factorization? Do you know what factorization is, right? What is the factorization of a number? A factorization of a number means you write a number as a product of two different numbers. That is what I mean by factorization. What is the factorization of polynomial? Factorizing a polynomial means you write down any given polynomial as a product of two other polynomials. That is the meaning of the factorization. Same is true for the world of math matrices. All right, so this is why. So sometimes this procedure, this entire algorithm, is so-called the LU factorization of A. In other words, you factorize any given square matrix A into product of lower triangular matrix times upper triangular matrix. So this is what I mean by LU factorization. So why LU factorization? Why LU factorization matters? That is because being able to have LU factorization can solve any given system of linear equations. Consider this system of linear equations. This is a system of linear equation that consists of n equations and n unknowns. I given a system of linear equations, and suppose that I had a LU factorization of this matrix A, then I am good to replace this A by L times U, right? Now, this is what I'm supposed to do. I declare U times X to be some other column vector C. C is defined to be U times X. Then this whole equation reduces to L times C equals to B, right? Now, what is the point of this? Then, well, you know, A is given and B is given, and therefore, and by LU factorization, I know my L. L must be a lower triangular matrix whose diagonals are all ones, and B is given. Therefore, so you can always solve this equation for C, because this is what it is. And by back substitution, C1 equals to B1, right? Now you have C1, and you plug in C1 here, and now you can solve C2, and up to, and you can find all the way up to Cn. So for this given LU factorization, you can systematically solve this equation for C. Now, once you have your C, now you solve U times X equals to C, this matrix equation for X. Then this X must be the solution of your original system. Okay? Just by, well, just, this is nothing but just applying the back substitution twice. That's it. So you apply back substitution once here, and another back substitution there, and that's it. This is how you get the solution X. Okay. All right. Just one more thing. Suppose you have any upper triangular matrix, U. And also I forgot to mention it, but there is one more assumption. And let us assume that all these diagonal entries of this upper triangular matrices, or upper triangular matrix, they are all non-zero numbers. These are all non-zero numbers. Suppose that you have such an upper triangular matrix. Then you can factorize this upper triangular matrix in this manner. D times B. So what is this? So here, this guy, these rows, these entries are obtained by just by simply dividing everything by U11, right? And the second, all these entries were obtained by just simply by dividing everything by U22, and so on. And you try to multiply these diagonal matrix to this upper triangular matrix. Then you can easily be convinced that this guy times this is going to be your original upper triangular matrix U. So this factorization is also possible. Okay, now why this factorization? Okay, let us suppose that LU factorization of A is possible. Then A can be written as L times U. But if I apply this factorization towards this upper triangular matrix, then I can say A is product of L times D times B. And so in other words, A can be written as a product of lower triangular matrix times diagonal matrix times the upper triangular matrix. And this lower triangular matrix has diagonal entries are all ones. And this upper triangular matrix has diagonal entries are all ones. And times some other guy D. Or some other diagonal matrix D. So this factorization is also possible. So as long as I have n non-zero pivots on this upper triangular matrix U. Sometimes we abuse sometimes we abuse the notation and we say this is LDU factorization because, well, V is clearly the upper triangular matrix. So instead of using letter V, so we prefer to use the letter U. So we say this is an LDU factorization. So this is what I mean by LDU factorization. All right, good. Sorry. LDU factorization is not always possible. There are two cases when LDU factorization is not possible. The first case is your matrix A is a singular matrix. That is, you can make by applying the forward elimination, you can make it to the upper triangular matrix, but whose diagonals are 0. Some of your diagonals equals to 0. Then your matrix A is singular. Then you cannot have an LDU factorization, right? And there's another case. Well, even if your A is a non-singular matrix, but sometimes you will encounter some 0 entries on the diagonals during the procedure of the forward elimination. In that case, how can you perform the LDU factorization? In case like this, A is 0, 2, 3, 4. This is clearly a non-singular matrix. Agreed? Because, well, even though it looks like I can apply, so even though I have 0 on the diagonals, but this is, well, just by simply exchanging the two rows, then this is clearly, well, yeah, I have the two set of non-zero numbers on the pivot. So this is a non-singular. So in such cases, I will need to exchange the order of the rows, right? So how do I exchange the order of the rows in terms of the matrix? I will define some mysterious matrix, square matrix, Pij. So what is Pij? Pij is a square matrix that satisfies these three properties. So what are these? Let me read one by one. Every k by k, k times k entry, k entries. So that means every entry on the diagonal equals to 1. If k is neither I nor j. So can you see the picture here underneath? So these are all ones, but jj entry and ii entry equals to 0. And this this dot, they represent all ones on the diagonals, right? And property number 2, ij entry and ji entry equals to 1. So again, go to this picture. This entry and that entry equals to 1. And otherwise, all the other entries equals to 0. So therefore, these guys are all ones except for this and this. And I have 1 and 1 here, and all the other entries, which I left it as a blank, must be 0, right? So this is Pij. I will call it as low exchange matrix. Why? Why is that? Because suppose that I have multiplied the n by 1 column vector to the right of this low exchange matrix. Then this times this is A1. So therefore, this one has to be A1, right? And so there is invisible A2 here, and A2 times this must be A2. And in the end, it goes on, But something strange happens here because AJ times, this is not 1, this one is 0. So AJ times 1 is 0, it's going to be 0. So everything equal, well, this means 0, right? But since I have 1 here, so 1 times AI, therefore, this entry is not AJ, but this one is now AI. And same is true for this. This number, which is on the I slope, is now being changed to AJ. And all the others they just carries over. Okay, they just carry over. So multiplying by this matrix, this low exchange matrix, is simply nothing but just exchanging these 2 entries. Okay. Now, generalizing this. What if I multiply this low exchange matrix not to a single column but a whole matrix? Then because of the exactly same logic, this is not, well, multiplying this is same as exchanging the order of these 2 lows, right? So this is the reason that I am calling this matrix as a low exchange matrix, because multiplying this guy to the left of any given matrix just exchanges the order. So this is, again, this somehow achieves the elementary row operations, right? This is also part of the elementary row operation. All right. Also, no. Something is, sorry. A product or multiple of n by n low exchange matrices is called a permutation matrix. Okay, all right. Low exchange matrix, a low exchange matrix is not a big deal. You can easily consider, you can easily imagine any low exchange matrix, but some low exchange matrices, this is somehow getting a little bit abstract. So I will try to be a little more concrete. Let me think of 3 by 3 cases. If my n equals to 3, then how many different low exchange matrices do you have? if n equals 3. There must be 3 of them, right? P1, 2, which is exchanging just row 1 and row 2, and P1, 3, which is exchanging row 1 and row 3, and lastly, P2, 3, exchanging the row 2 and 3. So I will have 3 different row exchange matrices. Now, how many different permutation matrices do I have if n equals to 3? Let me explain in this way. Well, multiplying bunch of permutation matrices is going to achieve a exchange of rows in some different ways. Therefore, the number of permutation matrices must be the same as the number of permutation of n set. Right? Because any permutation implies the exchange of rows of the matrix, right? Therefore, concretely speaking, if my n equals to 3, then I must have 3 factorial, which is 6. I must have 6 different permutation matrices. Agreed? Yes? Right? Okay. Okay, so let me try to write down all these permutation matrices. If n is 3, then the easiest permutation matrix is the identity matrix. Identity matrix is a part of the permutation matrix. Why? Because suppose that you multiply the same permutation, same row exchange matrices twice. Suppose that I multiply this guy twice. Then what do I have? Same thing, right? So exchange the ith row and jth row, and exchange the ith and jth row one more time is doing nothing, just undoes everything. So identity is always the permutation matrix. So therefore, I have one obvious element, which is 1, 1, 1. And I have 3 different row exchange matrices. 1, 2. And 2, 3. And 1, 2, 2, 3, and 1, 3. Oh, sorry. And I must have 2 other permutation matrices. That must be 1, 1, 1. This one must be the product of 1, 2, 2, 3, and 1, 1, 1. This one has to be the product of 2, 3, 1, 2. So okay, all right. So I have these 6 different permutation matrices. Sorry, I wasted too much time on this. But anyway, these are permutation matrices. They are not horribly complicated. You know what it is, right? Okay. Now, with some help of the permutation matrices, I can try a LU factorization of every non-singular matrix. How? Well, so if you encounter some zeros on the diagonals, on the diagonal of the matrix during the procedure of the forward elimination, then all you need to do is just try to permute the order of the matrix so that you do not encounter zeros on your way of forward elimination. That is the idea. Also, all permutation matrices have inverses. All permutation matrices are invertible, right? Because, well, these single matrix, a permutation matrix that consists of a single row exchange matrix, they are obviously these are invertible matrices, and the multiple of these invertible matrices are also going to be the invertible, right? So they are all invertible matrices. So one, 3, 4, 2, 5, 7, 1, 2, 5, 7, 2. So okay, let me try the forward elimination of this matrix for the elimination of this matrix. Sorry, so I changed my mind. Let me try the LU factorization of this matrix, if possible. Here, the first step is I need to eliminate these three numbers. To eliminate this guy, I need to multiply the -1 to the first row and add it to the second. That means for the lower triangular matrix, did I say this guy times -1 and add it to the second? Right? So second row, first column of the matrix L must be not -1, has to be +1. Right? So far, so good? Yes? These are entries that belongs to the lower triangular matrix L. Now, I multiply -2 to the first and add it to the third so that I can get rid of this guy. That means L 3, 1 must be, did I say multiply by -2? So has to be +2, right? And to get rid of this, again, okay. All right. So 1, 1, 1, 1, 0, 0, 2, 3, 0, 3, 5, -1, 0, 3, 5, 0. Okay, great. Now I cannot proceed for the elimination because I see the 0 on the diagonal. So there's many choices, but I try to exchange the row number 2 and row number 4. Exchange the row number 2 and row number 4. Then I have 1, 1, 1, 1, 0, 3, 5, 0, 0, 3, 5, -1, 0, 0, 2, 3. All right. But you will need to point out that row number 2 and number 4 has been changed. They haven't exchanged. Therefore, these indices, do you remember these? You have to remember these indices must represent the number of rows that is to be exchanged. So this number 2 is now is going to be number 4, right? And this number 4 is now is going to be should be number 2. And when this guy just carries over. So 2, 4, 1 is 1, 2, 3, 1 is 2, 2, L, 2, 1 is 2. Good. Okay. Now, also, I will need to remove this guy. How? By multiplying -1 to the second and add it to the third. I said multiply -2, -1, sorry. So that means it has to be plus 1, -2 to the second, and add it to the third. So L32 must be 1. And I have 1, 1, 1, 1, 0, 3, 5, 0, 0, 0, 0, -1, 0, 0, 2, 3. Okay, almost done. But I have one more trouble. I will need to exchange these two rows. So row number 3 and row number 4 must be changed. Therefore, every 3 must be now 4, and every 4 must be now 3. Okay, so L31 is 1, L41 is 2, L21 just carries over, and what is this? 4, 1. Sorry, not 1. 4, 2 is 1. Am I right? Are you following me? Yeah.
The first step is
You mean this set? No.
like there's hidden 4 times 4 matrix before that part. So should we have to change the row of the L things?
예, 한국말 하셔도 돼요.
연산을 적용을 할 때 저 L에다가도 L들한테도 왜 같이 적용을 해야 되는지를 잘 모르겠어요.
왜 L에다 적용 안 하면은 지금 우리가 지금 이거 끝까지 한번 보시겠어요? 거기 보시면은 이제 지금 permutation matrix가 I have 2 permutation matrices, and so the idea is this. So this is my original matrix, and I cannot proceed the forward elimination without application of the permutation matrices. So, okay. First, let me just finish this example. So. This is 2, 3. Hold on. Where was I? Yeah. This is my original matrix. And I have applied 2 permutations. The first one is to exchange number 2 and number 4. So number 2 and number 4. So this is the permutation that exchanges 2 and 4. And another permutation that exchanges 3 and 4. So 1, 1, Okay, so once you apply these two permutations to this matrix, then this guy must have the LU factorization. So what is L? Since the row has been exchanged in this way, just like this, therefore, these entries, these numbers must be the entries of the L of this matrix with permuted rows. So this is why I'm exchanging these row indices according to these permutations. 대답이 되었나요?
한번 더 생각해볼게요.
아, 예. 그래요? 1, 1, 1, 1. So 3, 1. So this one must be 1, right? And 4, 1, which is 2. So 2. And 2, 1, this is 2. And 4, 2. And so this is the matrix L of the permuted matrix. And what is my U? This one must be the U. This is the U of this entire permuted matrix. Okay. So this is the the point of this computation is, so if you permute your row, if you multiply the permutation matrix to the left of your original matrix, then as long as your matrix A is non-singular, then you can have a LU factorization. So this is these two, so multiple of these two matrices, they are called the P, and this is A, this is L, and this is U. So we say this is PA is LU factorization. So this is a more general version of the LU factorization. If your matrix is cannot have a LU factorization, then but you can still have the LU factorization if you permute the rows of your matrix. This is LU factorization, a PA LU factorization. Okay, good. Oh, I am running out of time, but I still have some more time. So. I have a square matrix A, and suppose that this guy has full set of pivots. So, well, if necessary, then we allow some row exchanges to matrix A. So suppose that, in other words, suppose that A allows PA's LU factorization, and it has all non-zero numbers on the diagonals. Then in this case, this system of linear equations, AX equals to B, has a unique solution for all possible choice of B. Okay, this is easy. Well, but because of this assumption that we have the PA LU factorization of the matrix A, and also you will need to notice that this equation, this matrix equation, is mathematically equivalent to this matrix equation. You know that P is always an invertible matrix, so therefore you multiply both sides by P, then you will get this. Or if you have this equation and you multiply both sides by the inverse of P, then you will get this. So these two guys are there mathematically equivalent, right? Now, because of this assumption, I am safe to replace the PA by LU. And also we declare U times X equals to C. Then first we solve this LC equals to PV for column vector C. This is always possible because, well, you will need to remember that this L is a lower triangular matrix whose diagonals are all ones. So because therefore, by back substitution, you can always solve this guy for C. And now next time you will need to solve Ux equal to C for X. This is also possible because it has full set of pivots. Therefore, the entries of this guy, they are all non-zero numbers. And again, because of the application of the back substitution, you can always find the X is always uniquely determined. So therefore, this one always has a unique solution. Okay. Okay. Great. We talked about the having full n set of pivots. Suppose that my matrix A is n by n matrix. This is, I have this system of linear equations. And in this section, we'll try to find the relation between being able to get LU factorization of this guy and having full n set of non-zero pivots, and A is invertible matrix. Those two things are very strongly related. In fact, they are mathematically equivalent. We're going to prove that. The first, I want to prove this proposition. The proposition consists of three different statements. The first is the uniqueness of the inverse. Suppose that A has two inverses, then you can easily prove that these two inverses, they are the same thing. Therefore, if inverse of A exists, then it must be unique. Let me prove A first. This first statement first, which is very easy. B and C are inverses of A. That means this equation is true, and these equations are also true. They are both true, right? Now we multiply these three matrices A, B, C in this order: B times A times C. And because of the associativity, I can choose to multiply these two guys first and this guy later. But A times C is identity. Therefore, everything is B. And if I choose to multiply B and A first, then B times A is what? Again, identity, right? So therefore, it has to be C. So B equals to C, guaranteed. So proof is done. Number two is somehow more complicated. Not that complicated, but yeah. So it says, A having full non-zero pivots is mathematically the same as A has an inverse. These two things are mathematically equivalent. So this is an if and only if statement. So therefore, I will need to prove those two sides, those two directions. Let me prove this direction first. I don't have enough time, sorry. So I'm just copy and paste the previous from the previous lecture. Well, so suppose that A has an inverse. If A has an inverse, then if we multiply this equation by A inverse, then X turns out to be A inverse times B. So in this case, if A has inverse, then the solution of the system is uniquely determined. X equals to A inverse times B. Now, let me prove the claim by proof of contradiction. Suppose that A doesn't have full set of pivots. Then, if necessary, by allowing low exchanges, then let me apply the LU factorization of P times A. Then, LU factorization enables to factorize this guy times the L times U. But this time around, since I don't have full set of pivots, therefore the last entry of this diagonal must be 0, right? Well, in this case, well, I am always good. So solving this equation for C is doable, right? Because, well, the diagonals of L, they are all ones. So C is uniquely determined, and this is given. But however, once you have your C, then solving this equation for X is impossible. Well, the solution is not uniquely determined because this guy equals to 0. That means, well, there is some ambiguity going on this variable xn, which means that it has no unique solution. Therefore, this equation does not have a unique solution. Therefore, this guy doesn't have a unique solution either, which is contradiction. And for the other direction, okay, I will continue the next lecture. Sorry.